All right, welcome back, everyone. My name is Katie Schultz. I have the opportunity to serve as your panel moderator for this next incredible panel that I've gotten to know over the last few weeks. I'm personally really excited to be here. I am first and foremost a mom to a 9-year-old little boss, and secondly, I am a dairy farmer. I farm about an hour north of here with my brother and sister. And we are excited and passionate to be a part of our local community and a part of the answers and the solutions to looking at environmental challenges moving forward. I also serve in the capacity on the Professional Dairy Producers Board of Directors. I've been in that role for the past 6 years and serving as their president for the past 3. And without further ado, I will introduce our panel here. We have academic researchers from the UW system and the University of Massachusetts Amherst who will present their findings related to phosphorus in the natural environment, describing relationships between phosphorus runoff and land use management, including how climate change affects phosphorus management and impacts the phosphorus management on water quality outcomes, and a case for transformative land use change. Each of our speakers I will introduce, and then we'll have them come up. We're going to try and keep moving our presentations right along to give you guys the most opportunity to have questions at the end. We had fantastic interaction with Sarah's panel, and so we want to make sure that we can get to as many of the questions and comments from you guys, so please make sure and continue to jot down and write down your questions as we go along. First and foremost, we'll have Dr. Val Klump, the former dean and professor emeritus at the School of Freshwater Sciences at UW-Milwaukee. His research focuses on nutrient and carbon cycling in lakes, and specifically study of dead zones in Green Bay. Dr. Klump has served as the board member on several regional and national organizations, including the U.S. EPA Great Lakes Advisory Board, the Wisconsin Sea Grant Advisory Council, and the International Joint Commission Service Advisory Board. Secondly, we have Dr. Tina Andargay, an assistant professor in the Department of Resource Economics at University of Massachusetts Amherst. She's an environmental economist, and her research focuses on various aspects of policy implementation as it relates to the enforcement and compliance within the context of water quality regulations. Dr. Andargay has recently studied effectiveness of local manure management regulations on dairy farms here in Wisconsin. We have Dr. Eric Booth, a research scientist with UW-Madison with a general interest in the intersection between land, water, climate, and humans. His research approach is transdisciplinary and collaborative. Dr. Booth's research topics include agricultural ecosystems, stream floodplain restorations, and the impacts of climate and land use on water quality and flooding. And last but not least, we definitely have a strong finish to our program with Dr. Randy Jackson. He's a professor in the Department of Agronomy at UW-Madison. He co-leads the Wisconsin Integrated Cropping Systems Trial, a 32-year-old experiment in Arlington, Wisconsin. Dr. Jackson is a co-lead on Grasslad 2.0, a USDA-funded project working to transform agriculture in the upper Midwest to a system that supports profitable farming practices while at the same time preserving and protecting our state's critical resources. Without further ado, please help me in welcoming Dr. Val Klump.
Thanks, Katie. As you know, the Clean Water Act was passed about almost exactly 50 years ago, and we no longer have this problem, that is, rivers catching on fire. And the Clean Water Act did a reasonably good job at controlling point source discharges, but one of the things that was probably not very effective at was dealing with the whole non-point source issue. And for example, this image was taken just recently at the western basin of Lake Erie. And a massive cyanobacterial bloom. In fact, there's a little white speck there as a 1,000-foot freighter going through that bloom. And this particular problem is actually throughout the Great Lakes in numerous places, including most recently on the southern shores of Lake Superior. But in Wisconsin, ground zero for this problem is Green Bay. Green Bay is unique in that despite the fact that it only is less than 2% of the volume of Lake Michigan, it receives 1/3 of the total phosphorus load to this system. And as a result, it's been hyper-eutrophic for decades. And more recently, we're beginning to see the increase in the cyanobacterial blooms, not only in the Fox River, but up along the eastern shore of the bay as well. And one of the consequences of excessive algal production, of course, is when this material sediments out and begins to decompose, particularly the fact that the Green Bay is a very efficient particle trap. Probably in excess of 70% of the material that goes into Green Bay stays into Green Bay. And during the summer, when the lake stratifies, that sort of caps the bottom water off and seals it, sequesters it from oxygen exchange with the atmosphere. And decomposing algae reduces the oxygen concentration, in some cases, to almost zero. And the formation of so-called dead zones, which have impacts on the food chain, on the benthos, and even potential fish kills. And it's received, when we first came out, it received a fair amount of press, none of it very good, some of it by our keynote speaker, I might add, Dan. And the question is, okay, what is the phosphorus load to this system, and how much are we going to have to reduce it in order to improve water quality? Dale Robertson shared this data with me earlier this week. By the way, there's a lot that goes into these plots in terms of producing individual data points. The bottom line on this graph, though, is the little bars at the bottom are the point source discharges from the lower Fox River. The pink area is the non-point source runoff. The TMDL for Green Bay indicates that we'll need to reduce phosphorus by as much as 40%. So the question is then, how do you do that? Where does it come from? The DNR's TMDL implementation plan says that the major source of reduction is going to come from agriculture. Now, this is in the lower Fox River Basin, and it's not a small reduction. It's 80%. And that's not going to be that easy to do. So where is it coming? Obviously, it's not uniformly distributed across the watershed, and this is SWOT modeling work by Paul Baumgart and Kevin Firmenich. Kevin is here today. Showing the various hotspots in the lower Fox River in particular. So obviously any management strategy that we put in place has got to deal with these. The best effective is to go after areas where we have very high phosphorus yields. And the phosphorus index was mentioned earlier. A phosphorus index of 6 would be off the charts on this plot, just so you know. One of the things that Paul and Kevin said, okay, if we implement management practices in this watershed, what benefit can we derive? And using a baseline of 90% conventional till, which is moldboard plowing or aggressive tillage, they said if you reduce that conventional till to 10% from 90%, put in 50% reduced till, 40% no till, you would gain about an 11% reduction in the phosphorus load to the system. If you have cover crops to that, you're up to around 18%. It's only until you get looking at reducing soil test phosphorus in the system that you get significant reductions in the phosphorus load yields from this watershed. And when you add in, on the order of 30%, taking phosphorus levels back to 1970s. You can add conservation tillage practices on top of that, and you can get close to, or maybe even in advance of a little bit of 40%. What benefit will that be to Green Bay? We have a coupled biogeochemical hydrodynamic ecosystem model in the bay, which takes the loading from the river and translates that into hypoxia, into chlorophyll algae production. And basically that model says that for a 35 to 50% reduction in the phosphorus load, you'll see anywhere from a 16 to 30%, say, reduction in the average summer chlorophyll concentration. In other words, the bay is responsive and fairly rigorously to reductions in nutrient loading. And my feeling is that the bay actually will respond really quickly if we were able to attain this. Well, of course, our climate is going to get warmer and wetter. This is downscaling data from the Center for Climatic Research here at Madison. Excellent work. And obviously, one of the course we all know is that it's going to be wetter, and that wetter is predicted to come in more into frequent, intense rain events. Green Bay is no different than almost every watershed, and that is loading is heavily event-driven. And here's the calculations by Kevin, basically saying that in excess of 70% of the total phosphorus and the total suspended sediments that are entering the system are derived from those dozen or so days it rains in the system. So any management strategy you have in the watershed has got to take into account the event nature of the loading to the system. What about climate change in general? And Kevin and Paul also looked at a variety of climate change scenarios. Now, these are all sort of business as usual climate change scenarios, which looks like business as usual is going to be more the fact than not in any case. But they looked at a range from relatively low warming, 2 degrees centigrade by the middle of the end of the century, to much warmer and wetter conditions. The bottom line is that all of these climate change projections using current management strategies, in other words, nothing changes on the landscape. We're doing exactly what we're doing today. The only thing that changes is climate. The phosphorus loading goes up. Climate is driving the system in the wrong direction. What about hypoxia? The Green Bay Met started back in the late 80s. John Kennedy initiated it using an oxygen sensor in the lower end of the bay. It's in relatively shallow water. It's in bottom water. So it's not a great indicator of hypoxia, but it does tell you probably the conditions that are occurring hypoxia further up in the bay. And the great thing is it's a very long-term record. Two things jump out of this. One is that in recent decade or so, it looks like hypoxia is becoming more of a problem in the bay than it had been in the past. The average time period over which hypoxia is a problem ranges anywhere from 6 to 10 weeks. That's pretty much the stratified period in the bay, and it depends heavily on weather and the wind conditions, et cetera. One of the projections, of course, for climate change is a longer growing season, maybe by as much as 6 weeks, which also translates to a longer stratified period. And you can make a simple, back of the envelope calculation to say, if stratified period was, say, a month longer, how would hypoxia change? And you can see it would get, significantly worse. The 1 year in which we had the longest hypoxic period was over 14 weeks, was in 2005. And just coincidentally, it's the only year in which we actually saw a fish kill right at the point there near Dykesville, where tens of thousands of round gobies were forced up on the beach due to cold, low oxygen depleted water. So the bottom line then is that we're looking to get a 40 to 50% reduction in this watershed. That is not going to be easy, period. The good news is the Bay will respond, I think will respond relatively quickly to improvements in water quality. Climate change is working against us probably, not for us. But the bottom line really, I think the take-home message from Kevin and Paul's work is that in order to obtain anything close to a 40% reduction, the key is reducing soil test phosphorus within the watershed to the point of where it was probably back in the 1970s, and certainly to the point where the crop requirements, the application does not exceed the crop requirements. Back one. Long-term data sets are absolutely critical. And all the plots I've shown you have a tremendous amount of long time series data embedded within them and under them. Green Bay happens to be one of the better monitored systems in the Great Lakes. And the key there is, ultimately what do we want to do? We want to predict the future. In order to do that, you have to have a good understanding of the dynamics in the system. So you can build a model that incorporates those dynamics that is relatively rigorous. But key to that, building that model, is having that data. And that data means that you can verify that model, you can calibrate that model, and see whether it makes sense. You can test it against existing and future conditions. There is good news in Wisconsin, I think. There's a lot going on in this watershed, and I think you'll probably hear about more of it later in the panel from others. But in any case, I think there is good news going forward. And of course, this work, is a cast of hundreds practically. I'd like to make a particular shout out to Dale Robertson, who's here today, and Kevin Furman, who's here today, and Paul Baumgart for the work they have done in the watershed, which is where the rubber actually meets the road. So thank you very much.
All right, Wonderful. That was a lot of information. I'm excited. I hope you guys have some of your questions written down, and we will be opening that back up as soon as we're done with the rest of the presentations. Without further ado, help me in welcoming Dr. Tina Andarge.
Hi, everyone. I want to start by thanking all of the organizers, especially Anya, for making this happen, and thanking Katie for moderating, and the other panel members. Today, I'll be presenting some work on non-point source pollution policy in the context of Wisconsin dairy farms. This is joint work with Maren Skidmore and Jeremy Foltz. Maren was a graduate student and a postdoc at University of Wisconsin-Madison. She's now at University of Illinois, Urbana-Champaign. And Jeremy Foltz is a professor in the Agricultural and Applied Economics Department at University of Wisconsin-Madison. So dairy is central to the economy of Wisconsin. It's central to the culture and the landscape as well. Estimates from 2017 find that it accounts for about 45.6 billion of the total industrial sales. So that's just about under half of the total value for agriculture and about 7.1% of the total industrial sales for the state. So it's an important part of the local economy. At the same time, non-point source pollution is responsible for most of the impairment to Wisconsin's water bodies. And so there's growing scientific evidence that dairy farming is a key contributor to poor water quality, which is detrimental to both human and environmental health, as well as tourism and recreation. And so the correct policy response is being debated at various levels of government. As this push for more regulation is happening, farms are going bankrupt at a high rate. So there's this concern that we're putting additional burden on farms when they're already vulnerable. And so this highlights the importance of scientifically backed analysis on the effectiveness of different policy responses. And this is important because we don't want to ask farmers to do something that doesn't work, so we want to know what works. And so that's what we set out to do here. We attempt to make a dent at this task. First, we examine whether local manure management regulations impact surface water quality, and if so, which regulations are effective at improving water quality. And our approach involves in-depth interviews with local and state policymakers and collecting data on county ordinances, on pollution data, and other county and watershed characteristics. And I'll give you some spoilers of our main findings before I discuss the paper in more detail. Our main finding is that water quality is better in watersheds with some county manure regulations. Particularly, nutrient management plans are effective at improving water quality, so are Silurian bedrock rules. The effects of manure spreading standards and prohibitions, however, are less clear, and I'll discuss that a bit more later in the presentation. All right, so let's get started. There's a large economics literature on water pollution. There's a branch of the literature that examines point source pollution policy, so policy governing industrial and municipal sources, for example. Or it could also be point source agriculture, such as CAFOs, which are regulated under the Clean Water Act. And what the literature finds is that CAFOs impair water quality, but the Clean Water Act mitigates their impacts. There's also developing literature on non-point source pollution policy. And non-point source pollution is responsible for about 82% of the impairment to Wisconsin's rivers and streams and 57% of the impairment to the lakes. And I think that was mentioned earlier in one of the previous talks. And so that's what we focus on in this paper. State Code Chapter 151, or NR 151, governs runoff management for the state, and DATCAP and DNR have enforcement power. In recent years, however, several counties have also passed county-level manure ordinances, which give them enforcement power. So when a county enacts these ordinances into their county code, the county conservation department gets the authority to enforce these regulations locally. Otherwise, all enforcement activities must be carried out by state agencies or federal agencies. So the variation here is not in what is enforceable, and NR 151 applies to all counties. The variation is in who can enforce it. Counties that have enacted it into their county code can enforce these regulations. And so we asked the question, does the county having enforcement power improve surface water quality? And if so, which exact regulations that it's enforcing is actually improving water quality? And to answer this question, we constructed a data set of county manure ordinances since 2008 all the way up until 2020. And for reference, the last update to NR 151 was in 2010. And this data set is developed by my wonderful co-authors and in collaboration with both county conservation departments and state agencies. And they document more than 40 ordinance characteristics. And what we focus on in the paper is manure spreading standards and prohibitions, because we expect that these rules would have a more immediate impact on farmer behavior and subsequently water quality as well. And specifically, we focus on manure management prohibitions, the 6 standards from NR 151, NMP requirements, and certificate of use requirements. We also examine slurry and bedrock regulation. So in 2018, the state passed stricter spreading regulations for the 16 counties with slurry and bedrock. So in these counties, any field with slurry and bedrock must develop a nutrient management plan before spreading manure. And these spreading requirements are more stringent in areas with shallower soils. And to give you a sense of what our data looks like, this is a table with the percent of counties that have enacted specific ordinance characteristics. And we have the percentage for both 2010 and 2020. And you can see that as the years pass, more and more counties are enacting these into their county codes. Okay? And so we combine this ordinance data with data on water quality from the water quality portal, and specifically we focus on ammonia and total phosphorus concentrations. And then we also obtain data on CAFO and dairy farm operations and locations. We also have data on weather, point source permit data from the National Pollution Discharge Elimination System, and crop cover data as well. And we combine these data sources to construct a HUC 8 level panel data set that spans 2008 through 2020. And we estimate an econometric model in which our goal is to isolate the impact of these local manure management regulations on water quality. And to isolate that impact, we have to control for other things that may potentially impact water quality. So here we have what we're interested in, which is the ordinance environment, and I'll kind of discuss that very briefly in the next slide. But we also include controls for other things that may impact water quality, such as precipitation, temperature, crop area, the number of farms within a HUC 8, the number of non-CAFO point source pollution contributors, and the number of CAFOs as well. And we also include fixed effects, which help us control for things we can observe, but may potentially impact water quality. And so to capture the ordinance environment within a HUC 8, so remember these county codes are at the county level, but our unit of analysis is the HUC 8. So to kind of capture what the ordinance environment in a HUC 8 is like, what we do is we count the number of farms within a HUC 8 that are in a county that have any of these ordinance aspects enacted into their county code. So for example, if we take the nutrient management planning requirement, we'd count the number of farms within a HUC 8 that are in a county that has that requirement in their county code. And that would capture the ordinance environment for the HUC 8. And we also calculate the share by dividing that count by the total number of farms within a HUC 8. And so what we're finding, so this is a coefficient plot of the estimates of the parameters we obtained from estimating that model I showed you earlier. The points correspond to the point estimate, and the bars are the 95% confidence interval. So if that confidence interval contains 0, then that ordinance aspect has no statistically significant impact on water quality. if the coefficient estimate is negative, then it reduces ammonia concentration or it reduces phosphorus concentration. So in blue, we have the estimates for ammonia, and then in maroon, we have the estimates for phosphorus. And what we can see is that nutrient management plans right here lower ammonia concentrations, specifically requiring one additional farm in a HUC 8 to adopt a nutrient management plan lowers ammonia concentration in that HUC 8 on average by about 0.9%. Okay? Oh, whoops, how do I go back? There we go. And another thing that we're noticing is that Silurian bedrock rules lower both ammonia and phosphorus concentrations. But one thing that did surprise us is that HUC 8s in which more farms that have adopted a broader set of the standards, actually adopting that broader set of standards actually increases phosphorus concentration, which was kind of surprising. But when we looked into it a bit more, we think that it may be due to the tillage setback standard and the complex effects of no-till farming. So no-till farming reduces erosion and the delivery of sedimentized nutrients to surface water, but it also makes nutrients more available at the surface of the soil, and that may potentially increase the delivery of soluble nutrients into surface water. So it's not a straightforward thing that we're looking at. And then for all of the other ordinance aspects, we're really not finding much. They're all not statistically significant from zero, and I want to emphasize that these are near-term effects that we're looking at. So if we're looking at a more long-term effects, they may potentially have an impact on water quality. They also may not. We just don't know. And then I won't get into this in the interest of time, but we estimate several additional specifications. And again, we find pretty consistent results through the different specifications. And to conclude very broadly, what we find is that nutrient management plans improve water quality. And this is in line with the recommendation from agronomists and extension agents that nutrient management plans are a good way to get farms to reduce their fertilizer application and the risk of suboptimal spreading. And we also find that Silurian bedrock rules improve water quality, and we find mixed results for the number of standards that are adopted within a county. And I want to conclude by saying that what we've looked at here is the impact of these local manure management regulations on water quality, but we think it would be great to actually examine the impact of these regulations on farmer behavior and then link that to water quality. And I think that's a great area for future research. Thank you. Sorry, I went over time.
All right, lots of things to think about and different ways to approach our topic at hand here. Without further ado, let me introduce Dr. Eric Booth.
Got my timer too. That gives me some credit, right? Okay, so thanks so much for the invitation to speak today. I'm really excited about the gathering in general and talking about phosphorus, and thanks to Katie, the organizers, the panelists. So I'm going to give kind of my perspective on where we've been recently in regards to phosphorus management in the state of Wisconsin. And actually, this is the wrong slide deck. There we are. Thank you. So I'm going to focus on kind of recent trends in what I'm calling the major drivers of phosphorus loss to waters of Wisconsin. And I just want to mention that this is going to be primarily focused on ag, and I think that was framed well in the previous talks, but I'm happy to take questions if there are some related to urban. So without getting too much into it right away, I do want to make the point that there has been progress in recent years, and I want to just highlight a few of those that are top of mind for myself. And there are new management and compliance tools that we've already heard about, focusing more on non-point. There has been more adoption of BMPs, best management practices. One that I'm particularly excited about is more farmer-to-farmer knowledge sharing and these watershed councils that have emerged. A little bit further back, we peaked in phosphorus fertilizer use back in the 80s and 90s, and that's slowly coming down. We're not feeding as much phosphorus in feed to dairy cows compared to about 30 years ago. And then another one on the urban side is there's less phosphorus in our municipal wastewater treatment plant effluent. And again, that was highlighted in an earlier talk. So I don't want to diminish those progress points with the rest of this talk, but I do want to make the point that the scale of progress has not matched the scale of the challenge that we face when it comes to phosphorus in the state of Wisconsin. And I think, again, that was highlighted in an earlier talk with the TMDLs that are ongoing in the state and the impaired waters that we have. And in general, this goal of around 50% reduction in phosphorus, at least. There's other areas that are even needing more than 50%. And so why is there this progress story and this kind of frustration story at the same time? And I would argue that there are many driving factors that are working in the other direction. And also complicating this is things like legacy phosphorus and time lags, just kind of inherent in the system. So I'm going to go, again, real quickly through some data sets highlighting these different driving factors. And just before getting into the data, I want to just go through each factor one by one, and this will be a little bit of 101. But I start with rainfall. It all starts with kind of that singular driver of runoff. If there's no rainfall, if there's no runoff, there's no phosphorus issue. But of course, that's not the case. So the more rainfall, the heavier the rainfall, the more we would expect to lose. Then there's disturbance of the surface soil. So more disturbance, more loss. And I'll show some data on that. Ground cover. More ground cover that we have throughout the year, the less P loss we would expect. Infiltration. So this is again related to runoff. If we can infiltrate more of that rainfall, we're going to have less phosphorus loss. And this is a diagram kind of nicely showing how infiltration can be enhanced with more perennial systems with their extensive root zones. And then another obvious one, slope. Steeper the slope, the more phosphorus loss. Again, we can target practices then to steeper land, knowing that. And finally, some new data that I'll show you here in a second, getting at a driver that doesn't get talked about, I feel like, as much as some of these other ones, even though it was mentioned in some earlier talks. But this idea of the supply of phosphorus. How is the supply of phosphorus changing through time? Are we applying too much? Is it a positive balance? Are we accumulating phosphorus in the soil? That certainly can impact and increase the risk of more phosphorus loss. So I'm going to go again through that list again and show you in one slide each my best snapshot of what's going on. So again, no surprise with rainfall, we are seeing more annual rainfall in recent years, more frequent heavy rainfall events. These are showing some of them in the last decade or so. Whoops. And we're also seeing this in days with rain greater than 1 inch. So we have really big rain events increasing in frequency and even some of the smaller ones. And this is, again, increasing the risk of runoff of phosphorus. When we think about broadly, land composition has changed in the state recently. This is from the USDA Ag Census. I'll be showing a lot of data from that great resource. We have seen more corn and soy come into the state in recent years. Sorry again, wrong button. And that has been mainly expanding in our southern region, but as dairy has been consolidated in certain parts of the state, commodity corn and soy usually replaces it. We're also seeing less hay and haylage as dairy rations are turning more to corn silage, and then less pasture. And so I show these in pictures on the left to just give you an idea of the relative ground cover associated with these systems. And thinking about the idea that we're expanding corn and soy, these are inherently more erosive systems. On the conservation practice side, we are seeing some progress, some moderate progress on things like no-till or conservation tillage. And it is increased in the last 2 census data sets, and it averages about 22% of the cropland in the state. And I know there are some complexities associated with no-till and phosphorus loss, but certainly this is going to help on the erosion side. But it's moderate. It's still only about 22% of the landscape in no-till at statewide. Cover crops, similar story. There's definitely been a lot of discussion and excitement around cover crops. There's been some new data sets coming out looking at how they've expanded using satellites, which is exciting. And you can highlight some certain parts of the state that have seen more in recent years than others, so the ones in blue here. But again, talking about the scale of the progress relative to the scale of the challenge, we're only at about 6% of our cropland acres in cover crops right now. The last category I'm going to spend a little bit more time on, just because this has been some recent synthesis that I've done, actually like literally in the last 2 days. But looking at the mass balance of phosphorus at the county scale over the last 20 years or so. And real quickly, all we're trying to do here is I'm playing an accountant of phosphorus at the county scale. I'm looking at the inputs, I'm looking at the outputs, and trying to make sense of the balance that remains. So major inputs, again, real quickly, fertilizer is going to be a big one that we bring in. Depending on the characteristics of the livestock herd, we might be bringing in feed to support the demand of that livestock. And again, depending on that balance, we might be exporting crops if there's sufficient crops available. And then another big export are the livestock products. So we're talking about milk and meat. All of these different components can be quantified at the county scale, primarily using ag census data. And I can talk about data all day long if there are questions on this, but I'm just going to stop there. The last export piece of this, though, is really important. It's the stream export. This is the source of our water quality impairments. But you'll notice it's relatively thin line here. It's orders of magnitude less than all of these different fluxes kind of coming in and out of the watershed. So how are we doing? Well, it's a little bit of a mixed bag. And just to set the context a little bit before I explain these maps, we need to recognize, as other speakers have already stated, we have a legacy phosphorus issue in our state. When phosphorus fertilizer started getting relatively inexpensive in the 50s and 60s, we used a lot. And that has added to the supply of phosphorus in our soils. And so that's what's shown on the top here. This is from 1964 to 2009, statewide. So we're dealing with this legacy P, and the goal here is to start drawing it down. So most counties actually have shown recent phosphorus depletion, and that's a good thing in terms of reducing that runoff risk. But we do see some counties here highlighted in red and orange that have been accumulating. And if we actually look at the trend of the accumulation rate, it's accelerating. And so some areas that pop out are northeastern Wisconsin and maybe Clark County. So these are particularly intense from a dairy production standpoint. So these are becoming areas more prone to runoff of phosphorus due to this imbalance of phosphorus. So accumulation rates, again, negative and declining in some of these more commodity crop regions, rates increasing, so we're accumulating at a faster pace in these dairy-intensive regions. And that, this is reflected in moderate increases in soil test phosphorus, so that's a little bit of validation for this method. But it's really important to keep in mind, excessive applications, this isn't kind of excess spread uniformly across the county. There are hotspots, and there are also hotspots in time, because you can think of that excess potentially being manure applications. And that risk of runoff associated with the manure is punctuated at different points in time of the year. And this is, again, something that Val mentioned. We are seeing in places that we monitor about 50% of the annual load coming in only 10 days. So if we have this excess manure in some regions, it's not, again, being uniformly applied everywhere. It's representing kind of a short-term risk and a long-term risk by building up the soil P. So where do we go from here? I'm going to kind of tee it up here for Randy to talk about some more innovative ideas to grab onto potentially. But the main message, again, is the progress just has not been enough and quick enough to overcome some of these other factors that are working in the other direction. And so the question is, how do we get off this treadmill of frustration that I think a lot of us feel when we think about phosphorus and when we look at data sets that we have monitored of this runoff in our streams? So I would say if we really want to reach our water quality goals, we need to substantially scale up low disturbance, perennial cover with lower and more balanced nutrient applications. And I think we have this ability to experiment and innovate. And Randy's going to talk about a project that we're working on called Grassland 2.0, but we know we can use tools to look at the relative differences in these systems. And clearly there are some that outperform others. And specifically, this is a case of a farm in western Wisconsin looking at how managed grazing compares to other systems. So I'll leave it at there and happy to take questions here in a minute.
All right, wonderful. And without further ado, we're going to close out the presentation part of our panel with Dr. Randy Jackson.
Thank you, Katie, and thank you to the organizers of the event, especially Anya, who did all the legwork, that is, from my perspective, did all the legwork, and I really appreciate the time and energy put into it. I want to talk about this Grassland 2.0 project a little bit in an effort to talk about solutions. You know, we spend a lot of our time and energy. It's amazing how much time and energy and resources we spend, how many programs there are, how many billions of dollars we spend. As my old colleague Josh Posner, who passed away 7 or 8 years ago, used to say, how much time and energy we spend trying to make the world safe for corn and soybeans. I want to be clear when I talk about Grassland 2.0 about some things here. I mean for this talk to be disruptive and to irritate people. I am not here to point fingers at anybody in particular. I am not here to blame farmers. I am not here to undermine the amazing work that agencies and NGO staff and university folks and farmers do to step up to the problem. You've heard a lot already today about the amazing work that's being done, but you just have to look at the posters and hear from the talks that it's not working. We're not going in the right direction. The phosphorus loading is getting worse. I mean, Eric showed that it's spatially different and complex. I get that, we need that, that's important. But the water quality is not improving, it's not getting better. And if we just focus on phosphorus and don't think about nitrogen and don't think about carbon and don't think about biodiversity and don't think about farmer livelihoods and a diverse, equitable, just agricultural system holistically, if we don't do those things, we're not going to get anywhere. We're going to be right where we are now in 10 more years. So I could spend the next 15 minutes showing you a lot of data, but my grad students told me, nobody listens to data anymore. Nobody cares. They know what they know. So I want to talk about this project that is meant to be an effort to build a movement from the bottom up. It's meant to fan the flames on conversations around the state and beyond to try and get folks to demand more from our policies and our regulations and our society in general. We've got to stop focusing, I would argue, on individual behaviors and focus on systemic change. And that's what Grassland 2.0 is trying to do in more or less convivial ways. So we have a lot of folks who are associated with the project and the program that maybe don't plant the flag as strongly as Randy does, but hey, that's my job to come out here and rattle cages and plant the flag. So let me start with my takeaway message. We will not meet our water quality goals or any of those other goals without transformative land cover change. We're not going to fix the current system. It's just not going to be fixed because it's fundamentally flawed. It's a fundamentally leaky system. Annual cropping systems are fundamentally leaky. We've spent thousands of years breeding the plants to put their energy above ground. We harvest that energy. They put very little below ground. Then we come in and churn the soils. Even when we don't churn the soils, they're leaky. And they're going to continue to be leaky. When we come in and add more nutrients on top of that inherently leaky system, it's no chance. It's a huge sieve. It just is. People have done amazing work over the last 100 years to try and make them less leaky, but it's not going to happen. All right. Grassland 2.0 is the notion that we have to have an agricultural system that more closely resembles the function of the original prairie. I made a promise to some people. I would not come here and say we need prairie wall to wall in the upper Midwest, but we need ag systems that more closely resemble the original prairie. These are not going to get us there. We're overloading and overwhelming the system. You've heard this already. Our health and well-being depends on an agricultural system that does at least these 8 things. Undisturbed soil. We just can't churn the soil up. Now look, we have to have pockets where we grow food for ourselves in gardens. We have to have areas that are more benign where we can grow some crops to feed ourselves. But we do not need to churn the soil to feed our gas tanks or to feed animals in confinement. We just don't. We need dense continuous canopies. We need few inputs into the system. We need deep fibrous roots. We need diverse communities because we're learning more and more that the more diverse the community is above ground, the more diverse the community is below ground, the microbes and that sort of thing, the more likely those systems are to accumulate and hold on to carbon and build organic matter and hold on to nutrients. You all know all this already. You've all taken grassland ecology. We need systems that are net energy gains, that build carbon more than they lose carbon. And as a result, hold on to nutrients and hold on to nutrients and provide habitat for biodiversity, et cetera. But it's not just enough to have perennial grasslands, because that's the equation so far. Those grasslands have to be thoughtfully and carefully and adaptively managed. We can't just put grasslands on the landscape and beat the hell out of them and try and squeeze as much as we possibly can out of them the way we do our current ag systems. We have to take care of them and nurture them. We need a land ethic. I wish somebody would have said that. As my friend over in the public health school, what's it called? The School for Public Health, once said, it's pretty sad that Leopold's legacy is a literary legacy and not an actual implementation, farming, agrarian legacy. A key part of the land ethic speaks to what Eric just talked about. We cannot stock the land with more animals than it can support, the end. I mean, we can talk all we want about NR 151, and that's all important. I'm not trying to dismiss all that. But the fundamental deal is we can only have as many animals on the land as the land can support. And when we talk about what it can support, we talk about holding on to the nutrients, building soil, not losing it, supporting biodiversity. That is going to be fewer animals than we have now. There's just no way around it. There are going to be losers in that situation. People are going to have fewer animals. We just have to come around to it. People are doing this now. This is the Cates farm. Most of you have probably been there. Dick and his wife Kim and son Eric and family probably host 2,000 people a year to come out and look at their productive, profitable farming system in the Wyoming Valley out near Spring Green that has what has recently been classified by DNR, a Class 1 trout stream running through it. Anglers come out by the droves, hunters come out. This is multifunctional agriculture in agroecology speak. It can happen, it's happening. Why aren't we making it happen more with our policies and our narratives and our norms? We have to go this direction. Well-managed, grazed grassland is our best and maybe our only chance of mitigating climate change with agricultural soils while cleaning surface waters, groundwaters, enhancing biodiversity, and on and on and on. We have to promote it in our rules and regulations and policies. It's not just for the small farmer. That's the pushback I often get. This is the Opitz farm down in outside of Mineral Point. I don't know how many animals they have these days. I think they have about 2,000 animals, maybe a little bit less. They use well-managed grazing. They have enough land to support those animals. It's incredibly productive. It's a model system. It provides for us. It's profitable. Tom Kriegel spent 15 years of his life as an economist at UW-Madison tracking financial data, showing that real-world data, the grazing system on a per-cow basis is almost twice as profitable as a confinement system. So why don't more people do it? Because my university pushes and promotes confinement, modernization. You can get more. Push it. Get big or get out. Squeeze more out of the system. We've got to stop that. This doesn't mean this is not going backwards. This is finding the right place. Okay, let me try and stop pontificating so much. It's not just Tom's data. This has been found over and over. Animals that are raised in rotational graze systems are healthier, they last longer, they're just as productive when they enter a lactating herd. The land is better for it. Folks who manage them claim to be happier. The cows claim to be happier. Kate Kreutzinger, who's a scientist at UW River Falls, told me about a project she did where they actually looked at the brains in the cows when they were fed TMR or when they were fed pasture. And they know, because they've calibrated all this, that when they're fed pasture, the happy part of their brain lights up. Okay, that's enough. Too much data. All right, you all know this. I'm not telling you anything. Grassland agriculture undermines the current paradigm, which is extracting as much as possible out of the system so that a few can make an amazing amount of money. We have to come together as people and fight this. They are going to fight tooth and nail against transformative change. We have to figure out how we can fight this. All of this is promulgated because the powerful have convinced even folks who are not doing well and benefiting from the current system that there's one way to do it and a good way to do it. And being a good farmer means getting big or getting out, squeezing as much as you can out of the system. We have to undermine this narrative. So, transitioning from extractive to genuinely regenerative ag will be costly and painful, but hey, we're at costly and painful now. Infrastructure transition costs will be high, but critically, they will be transition costs, not long-term, we're going to have to keep paying, we're going to have to keep paying, we're going to have to keep paying. Once we get the systems up and running and get people in place doing it, they work. They're ecosystems that function, unlike our current systems. We've got to change the narrative on what progress means. We've got to change somehow this perverse land valuation system that somehow makes land more valuable if you extract more out of it. And of course, we have to have folks who are willing to put their careers on the line. not really. I can stand up here and wave my arms and pontificate. I spent 20 years collecting the data, and that we don't need any more data. We need action, we need policies, we need regulations, and we need a new narrative where the starting point is agriculture is the solution to these problems and not the problem. I'll yield my time to Katie and invite tomatoes and whatnot here.
All right. Wonderful. I hope there's no tomatoes. I have a white shirt on, and that's not going to end well. So with that, I open the floor up for questions. Again, feel free to come up to the front and speak loud into the microphone so everyone can hear. And I think there's a lot of opportunity here, right? We need to look at different solutions that are sustainable for our economy, whether that's economically sustainable, environmentally sustainable, and socially sustainable. What do those solutions look like as we move forward as an entire sector? It's not, I can't echo enough. It's not a you versus me, it's an us coming together. It's the dairy farmers coming together with the crop farmers, with the research, with the policymakers. We need to figure out how to create a solution that works for everyone. Because if it doesn't work for everyone, we all lose together. I will start off with just one question, and I will ask that you each kind of take a stab at it, and then we'll take questions from the floor. So when we're looking at different, each of you in your academic life and looking at where the research has been and where we're going, where do you see the biggest gap that will help, that we need to fill in order to push us forward to the next level? Don't all take it at once.
We'll start at this end of the table and get better as we go the other way. I mean, the bottom line is that, the Clean Water Act was successful because it said to every point source discharge, here's the standard, you got to meet it. It didn't matter whether you discharged to the village pond or the Lake Michigan. It didn't matter what the assimilation capacity of the system you were discharging. Everybody had to meet the same standard. The problem with the non-point source issue is that we don't have a real standard. If you recall the plot I showed that Kevin and Paul produced that had the SWOT model, phosphorus yield, and there were some pink areas in there, those were identified as the phosphorus hotspots. The maximum value in those hotspots was 3 kilograms per hectare, which translates roughly to a pound per acre. The phosphorus index target is 6. It's way over where we need to be in terms of reducing nutrient inputs to the system. My feeling is that eventually, carrots are good, but at some point you're going to have to use sticks. We are all going to have to pay more for food. Food's too cheap. We're going to have to pay for it. I mean, in order to implement the Clean Water Act, we spent tens of billions of dollars per year to clean up our industrial and point sources. We're going to have the same level of effort, to clean up and do a better job in agriculture and urban runoff for that matter. Every time my neighbor, fertilizes the grass, he goes right across the sidewalk. I say, Joe, there's no way you're ever going to go grass on that sidewalk. Right? So it is, as Randy pointed out, there's a mindset that has to change. But my feeling is without some regulation, we'll never get there. We have to force ourselves to do the right thing.
Yeah, I would say that I think it's a combination of top-down rules and regulations that are geared towards really caring for people and taking care of their basic needs for food and clean water and stable climate and all those things. So you might say a way where we reward land managers for all the ecosystem services that they provide us. And there's all kinds of argument about the best ways to do that, but there has to be that signal from society that this is what we value and what we want you to do. And then I think that has to be coupled with, because as we all know, nobody just gets told what to do, rightly so. There has to be programs and systems like the producer-led watershed group, frankly, that bring people together, but maybe a little bit unlike the producer-led watershed group, kind of focus on outcomes rather than particular practices and that sort of thing, where the goals are set at a relatively small spatial scale, a watershed scale, and folks are incentivized to race to the top on getting to those goals. And there can be perverse outcomes and all that too, so we have to be careful with regulations and boundaries that help guide that. But I do think it has to be this combination of top-down, if you will, and bottom-up approaches to getting there.
I'll be short so we can get some more questions, but I'll maybe say a nerdy one, because I do think data can be useful. I understand the power associated with our narratives and kind of revising our identity as a state, but I do think we need to be better at collecting data. The Ag Census has been great for the type of work that I presented on, but that is even getting harder to get critical information. And so just basic things like how much livestock is in a certain area, and not even just at a county scale, but getting down to the actual point scale. We know very little about where livestock are on the landscape. So I think there's a lot we could improve to monitor these different driving factors.
So going off of what everyone else said, once we have effective policies and regulations, so I study enforcement, monitoring and enforcement and compliance, but once we have these regulations in place, we need to make sure we know what works in terms of monitoring and enforcement, so what actually improves compliance. And that's not always clear. Given a fixed budget, monitoring and enforcement budget, we need to know how to allocate those resources. And in order to do that, we need to know how effective each monitoring or enforcement activity is. And I think when we implement policies, it's also a learning opportunity to see what works. And collaborations between academics and people in the agencies could provide us an opportunity to learn what works in terms of monitoring and enforcement.
Excellent. Do we have any questions from the floor? Or I have a whole notebook full of questions I would like answered, and you guys are going to have to listen to those. So we'll take one here.
Thanks. In Portage County alone right now, there's 10,000 acres proposed for solar photovoltaic development, utility scale solar. That's just using existing market rates. Could we steer water money to tip the scale to bring more acreage into solar? And then what's the cascading effect on the production of corn for ethanol for gasoline?
Ooh, that's loaded. Who wants to take that one?
I don't know the answer to the last part. I know there's a lot of interest in how can we co-produce ecosystem services under solar. How can we maybe graze it? How can we harvest it, et cetera? People are doing that, elevating the panels. There's issues with keeping them clean, et cetera. These are issues that are not insurmountable, it seems to me. So I think incentivizing that as much as possible is a good idea. But what makes me really nervous and is related to this bottom-up thing, and if I had had another 5 minutes, I would have gotten to some slides where I regaled you with this approach that we're taking in Grassland 2.0 called collaborative landscape design, where folks in watersheds and local communities are being supported to come together and intentionally design and plan for what they want their landscape to look like, what they want out of their landscape, what they want their communities to look like. I think that's a really critical element that seems to be missing in the whole solar discussion so far. I don't spend much time studying that, but people in local communities do not want the power companies or the university coming into town and saying, hey, we're putting solar here. Isn't this great for you? Look at all the benefits. They want to come together and understand what the trade-offs are and come around to these ideas in a process we call placemaking, where they make the place themselves. And so I just want to put in a plug for whether it's solar or grazing or whatever the solutions we deem are critical are, that we empower those conversations. And I see the producer-led watershed group and the demo network that the NRCS runs as really great opportunities to kind of like channel money and resources to those local conversations and help them come up with these bottom-up solutions.
Yeah, that's a great point. I think there's a lot of communities that are forced to have the conversation of best land use and what does that look like in your community, and whether it's from an economic standpoint to a soil type standpoint to an entire environmental and social standpoint. What does that look like for your community? And I encourage you to get involved. These conversations are very real and happening very fast right now in our local communities here, especially around the Madison area. And so I echo what you said. I couldn't agree more.
Uh-oh, this is trouble.
Sorry. Hey, I'm too tall for this microphone, for one.
I've never had that problem.
Yeah. I'm Ben Lebowitz. I'm a student at the Nelson Institute for Environmental Studies here at UW. I'm also probably the biggest Aldo Leopold fan in this room, arguably. So I'm going to ask a question about that.
Those are fighting words.
Arguably. Anyone can talk to me about it if they want. Anyway, the latter half of his life, Leopold focused on the private landowner and those issues on private land, and really trying to find out if we could get, private landowners to make this ethical change, different relationship with the land and different practices. Do we think that we have the tools to ultimately change the paradigm in private land use? Or are we fighting against something that's, how difficult is the battle, really? Eric's graph at the end of his PowerPoint was pretty indicative about what practices work, what practices don't. So what's the battle like?
I'll just say really shortly that I think all farmers in Wisconsin have a land ethic that they think is responsive to Leopold's charge. I don't think any farmer wakes up any morning and thinks to themselves, how can I pollute the water today? I think every farmer in the state of Wisconsin is doing the best they can within the current system. The system is the problem. We have to change the system, and that will allow folks to take their land ethic and drive it in directions that actually result in more positive outcomes.
Yeah, I'll just add one quick thing. I think from my standpoint, researchers, agency folk, NGOs, I think we have a lot of power over the kind of potential realities that could happen on the ground. And I think sometimes implicitly we narrow that scope when we talk about the future of agriculture. And I think we are biased towards a system that is set with a single goal of boosting productivity. And I think we just need to challenge our implicit assumptions when we have these conversations about the future and really open it up to new ideas and transformative ideas. And so I think we can all play a role in expanding that conversation.
Yeah, I would just echo the comment in my circle, right? In my circle of dairy farms and farmers in general, the narrative is always you do the best you can do until you know how to do better. And until we have that established of what the next better is, we're continually striving for that. And it's not that anyone ever intentionally wants to do something to harm or pollute, but it's what can we do next? What can we do better? How can we continue to improve? And looking for that continued improvement, it's critical.
Hi, I'm a law student, and I also have a science background. And I've always found there's kind of a concerning gap between research and like policy implementation and like public participation, and like in complex issues like climate change and just any environmental issues. There's always data, but there's like a lack of translation into, I guess, the public sphere. And my question is, in your, I guess, experience, academic experience, what are some useful ways that you can kind of leverage the data you have to like result in better effective policy implementation, or just even better public knowledge about the issues and how they can participate in implementing those changes?
It's a great question. I guess from my experience, a lot of times agencies actually put out calls when they're interested in knowing the answer to a specific question. That kind of breaks the hurdle of they already want to implement this, you're just telling them what works. So that's one way to kind of get at that. But in general, making sure your work isn't just presented in front of academics, trying to get it out there to people who could actually use the results of your work, I think that could be helpful. Yeah, I think those are the two things that come to the top of my mind right now.
For me, it's through our educational system. So we have, I'm part of the Department of Agronomy, and like a lot of other production-oriented, well, there's the problem, production-oriented departments on campus, I think that we are seen as part of the problem, like I said earlier, and that's because we have been. And so until we offer a different approach and alternative to young people, in particular students, that shows that there is agriculture that can be part of the solution, and here are all the manifestations of it, and there's lots more negotiation and tugging and pulling to do, but there are solutions. People get excited, especially young people who want to be part of making this better. Young people today have been hit up one side and up down the other. They've been whipsawed around by a lot of bad stuff, climate change and COVID. They want to feel like there's hope, and there is. We have to get it out there and make it reality.
All right. I have time for one additional question, and this will be the last question from the floor.
I love getting the last word. My name is Erin O'Brien. I work for Wisconsin Wetlands Association. The data is really compelling, especially the pieces about, 59, 60, 75% of the problem is happening in a very short number of days in relationship to precipitation events. And that tells us that we need to be thinking not just about what we're putting on the land, but how water's behaving. And my question is, why are we not thinking more about hydrology? And loss of wetland storage, loss of floodplain connection, and the legacy. Thank you, Eric. Yeah, this question was for Eric for sure. But the legacy of so much hydrologic alteration, and the fact that we have so much opportunity to increase storage, increase infiltration, slow the flow of water, reduce energy and erosion, and it just doesn't seem like it's part of the conversation in this community. Thanks.
Great, thank you. Love hydrology and hydrology questions. Yeah, so I guess that it was just kind of maybe in the background of what I was talking about. Certainly infiltration is a key process for reducing runoff risk of phosphorus. So yeah, I mostly just talked about kind of perennial systems and their rooting structures, kind of opening up conduits in the soil for that rainfall to infiltrate. But certainly there's a lot of other ways that can happen on a landscape, whether it's wetlands, buffers. So yeah, pastures. Thanks. Yeah, I already talked about that. Yeah, so I hope it's in the background, but I think your point is well taken. It should be maybe forwarded a little bit more, especially in light of climate change impacts coming and more increasing frequency of heavy rainfall events. And so it's just going to be a new system, and it's constantly going to be reinventing itself, I guess, in the future as it gets warmer. So I don't know, Val, do you have anything to add?
All right. With that, we're going to conclude this panel, and I want to commend each of these fine individuals up here on tackling a topic that's hard, and sometimes it's messy to get our hands around, and it's, taking a look at the issue and taking a look at the topic from someone else's perspective can really help us to try and get a better, well-rounded look at it. And so I want to continue the conversation throughout the rest of the day to coming together to change mindsets, to look at how we can improve policy, regulation, and implementation through the entire system. And so with that, without further ado, I am not standing any farther between you and your lunch. If you want to head out and grab your lunch, the session here will start back at 12:30 promptly. and make sure to log on to the Slido and give reviews and comments so we can continue to improve this entire program for future years. And with that, thank you very much.